Der nächste Vortrag ist Performance of Augmented Reality Remote Rendering via Mobile Network. Und das Paper ist von Kai Börner, Arnulf Fuhrmann und Herrn Bösinger. Und der Vortrag wird gehalten von Kai Börner. Ja, und damit übergebe ich auch schon direkt an Sie, Herr Börner. Wir freuen uns auf Ihren Vortrag.
Ja, hallo, guten Tag. Ich würde den Vortrag jetzt auf Englisch halten. Fragen nehme ich sehr gerne dann auf Deutsch entgegen. Okay, so welcome to the presentation performance of augmented reality remote rendering via mobile network. My name is Kai Börner, and this work was created together with my co-authors Arnulf Fuhrmann and Michael Bösinger as a collaboration between Vodafone Germany and the TH Cologne. So first we start with a small introduction. So our motivation for our work was that over the last years, several augmented reality SDKs with markerless tracking were released. Every three main components of an AR app will be executed on the end device. In our example, a smartphone. So the tracking, the interaction, and the rendering will be completely done on the device itself. We have a high stress on the several components of the device, and the visual quality of the virtual objects is therefore limited. The user experience heavily depends on the available performance of the device at the end. So our idea was to move the rendering and the interaction component to a server by the usage of remote rendering. We decided us for an image-based approach in order to reduce the load on the smartphone as much as possible. The smartphone still does the tracking, the position, orientation, and the inputs are transmitted to the server. The system was realized as a mobile edge computing system. This means that the server is part of the local network or of the provider's network. So we do not need to involve the internet for the access. The goal of our work was to implement a remote rendering procedure for Unity augmented reality applications in order to increase the visual quality and the performance. Over the last years, several related work were done. In remote rendering, the work was already performed over 20 years ago. And during this time period, two key challenges were described. The first one is the interaction latency. That's the time between the user interaction and the display of the result. Depending on the approach, they are more or less affected by the interaction latency. If the client device does more of the rendering task, then it can manipulate the results in order to reduce the interaction latency. The second key challenge is the limitations of the networks, such as the bandwidth, the maximum data rate, and the transmission latency. The second key challenge can be handled by the evolution of networks. For example, the step forward from 4G LTE to 5G, or by the introduction of mobile edge computing. As I already mentioned, in mobile edge computing, the server is part of the provider's network. Ideally, it's directly at the mobile network tower. For mobile edge computing systems, also several work were released. For example, a middleware platform for collaborative applications where the data and the processing are shared between multiple users but are done on the edge server. Another approach for augmented reality applications could be to move the markerless tracking and the object recognition to an edge server in order to reduce the latency of them. So now we come to the system overview of our approach. So that's our system. We realized this with Unity 2018, and we tested two different network connections. The first one was a local Wi-Fi setup. The second one was an LTE lab network. The server renders the scene with the standard rendering pipeline in Unity. We call it legacy pipeline, and the client uses one of the new scriptable rendering pipelines. In the older version, it was called lightweight rendering pipeline. I mean, in the actual versions, it's the universal pipeline. The pipelines, the sub-pipelines are completely working independently from each other. They work asynchronously. So updates are processed as fast as possible. But if we have transmission errors, not the whole pipeline will be interrupted. Every rate in our system can be tuned independently from each other in order to optimize the latency or the stability. For example, the server can run without the rendering limitation, so it will render as much frames as possible. The video can be set, for example, to 60 FPS. This means in the end that not all rendered frames will be encoded, but this allows us to see which performance is still free on the server and to analyze the encoding time. The client can also use another frame rate, for example, 30 FPS, so that we have 2 video frames for the client. For 1 frame it will show, so that we have a backup frame if there are some errors during the decoding. So, as you see, the video encoding is one critical aspect in our work. The server renders like normal locally running Unity applications and renders into a texture. This texture is at the end copied to the separate video encoding units on the GPU. We can use therefore a native API like DirectX 11. The encoding is then done on the GPU on the separated units. This means in the end we have no copy of the texture between the CPU and the GPU, and also the other resources of the GPU, like the shaders, are not used for the encoding. So the complete performance of the server is still be available for the 3D rendering. The problem on this is that we are limited to specific formats which do not support the encoding of transparency. But we need it because the client blends the transmitted video in front of the camera frame with the real world. So without transparency, no real world. So therefore we include a chroma keying. So in the end, the server sets the unused pixels, which should be transparent to a specific color. For example, to black, the RGB value 000, and the clients set these pixels to transparent after the decoding. In order to have no problems with dark scenes, we also include a color brightness limitation or compression to have a protective area to the keying color. So in the end, for example, our minimum RGB value is 555 or 101010, depends on the scene. So we tested in our work 2 different prototypes. The first prototype was used for latency measurements in a rudimentary scene. The second prototype was used for frame time measurements by using a complex scene. We used the spotlight tunnel scene from Unity, and we compared the second prototype with locally running versions of the spotlight tunnel scene. So on the latency side, we take a look on the video and also on the audio latency. We compared also our client app with a VLC media player locally running on the server and on a laptop, which was also connected over the 2 different network setups. The reason why we choose the VLC player is that our media player component is also based on the same library, so that we can compare it, how good is the integration into Unity in the end. On the video side, the client app has a much higher latency than the VLC player. So in the end, this means there are many components for us, many options where we still can do some further investigations and optimizations. On the audio side, it's completely different. There we are better at the VLC player, but there are still but the latency is still too high, so we also need to do some optimizations on that. So here we have a demo video of our AR application. We tested the spotlight tunnel scene in 2 different versions. at an AR application and as a full screen application. If the video actually hangs, then you are able to find the videos on YouTube and you can watch them on that platform, or you can also find the videos on the web page from the TH Cologne's computer science group. So I try to describe what we can see in this video. So on the left, we have the lightweight rendering pipeline, and the image is overexposed. The reason is the used version of Unity and the AR Foundation, which has a problem with the linear color space, which results in the overexposure, but the linear color space is needed for the scene. On the right, we see the rendering pipeline, and this has some noticeable latency in the movement of the virtual object. So in the end, when the camera changes its movement direction, then the virtual object still uses for a moment the old direction, and then it's a little bit behind on the end. So here we have our frame time measurements diagrams from the test run. One test run was 60 seconds long, so 1 minute. And we have several aspects we can see here. So for example, when we have an interruption in our connection, then the client still shows the old frame and the frame time will increase. So these are the peaks, but we also lost many times 1 frames. So in the lower resolution, the local pipelines are able to render us more pictures. In the higher resolution, the remote rendering approach is faster than the local pipelines. So here's now the demo video from the full screen app. It's on a larger scale of the spotlight tunnel scene. And here we see quite differences between all 3 pipelines. So the lightweight rendering pipeline had the much worse lighting and less details than the other both pipelines. The remote rendering pipeline is able to achieve the same visual quality or even a better quality by a higher performance on the end. So here are the frame time diagrams of the full screen scene. And here we have on the higher resolution, the same effect like on the AR application. We are faster than the local applications. In the lower resolution, the lightweight rendering pipeline is still faster, but the visual quality is much worse in comparison with our approach. So as I already mentioned, we tested 60 seconds long, but we do 5 test runs totally directly after each other. So we have a runtime of 5 minutes tested. And modern devices throttle their performance under certain circumstances, like high load and a high battery drain. And this also happens to the local pipelines in our tests. The throttling can be about 30%. Our remote rendering approach has a better long usage performance in the end because there is less throttling. So lately in the 5th test run, our remote rendering approach was faster than the local pipelines. Another main aspect what we looked on in our work was the video bandwidth. So we thought that the AR app should be used less bandwidth because the number of used pixels is smaller. Many pixels are filled with the transparency color, with the color keying color, and we have no major changes inside of this area. On the right, you can see our measured minimum and maximum in our tests. And we have still some bandwidth free in the AR application. So the encoder was configured to 7 megabits. per second, and the application needs between 5 and 6. So in the end, we have still free bandwidth, and this will result in no coding artifacts. If artifacts can only occur due to transmission errors. In the full screen application, it's completely different. There we are using the complete 7 megabits. The encoder is exhausted, and in the end, coding artifacts can appear and also dropouts. The AR version can be transferred without these coding artifacts. So, what's our conclusion in the end? Our remote rendering proof of concept works. We were able to achieve a better frame time at high resolutions. But our performance was also better in the lower resolution for a long usage runtime due to the less throttling. But still further work is necessary, mainly on the video and audio latency, because we see only slight differences between the video and audio latency over our LTE network and over the Wi-Fi network. And the latency for the video was quite higher than for the VLC media player. Further investigations should also be done with 5G radio and the slicing feature, because with them we are able to fight against the second key challenge of remote rendering. We are able to achieve higher data rates, and for the first time, it's also possible to guarantee a minimum data rate and a maximum latency. So, thanks for your attention. Do you have any further questions? Please feel free to ask.
Okay, ja, vielen Dank für den spannenden Vortrag, Herr Börner. Und es sind auch schon Fragen jetzt über Slido reingekommen. Nochmal zur Erinnerung an Zuhörer, die jetzt vielleicht neu hinzugekommen sind, dass man über Slido Fragen stellen kann. Die erste Frage wurde auf Englisch formuliert. Are you running a custom photon server on your rendering PC or a remote server provided by Photon? Ich nehme aber an, obwohl die Frage auf Englisch formuliert wurde, dass Sie auch auf Deutsch antworten dürfen, wenn Sie mögen.
Ja, ich würde jetzt auf Deutsch einfach antworten. Also wir haben den Photon-Server ebenfalls auf dem Server, der das Rendering durchführt, ausgeführt. Also es war keine Photon-Einheit, die jetzt bei denen in der Cloud lief, sondern die lief dann auch lokal auf dem Rendering-Server.
Mhm. Okay, vielen Dank. Noch eine Frage von Anonymous. Denken Sie, dass Ansätze der künstlichen Intelligenz eine wichtige Rolle beim Remote Rendering sind?
Also meiner Meinung nach könnte ich mir sehr gut vorstellen, dass das in Zukunft ein zentraler Bestandteil ebenfalls wird für die Remote Rendering Systeme. Denn gerade mit der Hilfe von KI können wir halt nochmal ganz andere Manipulationen auf den Geräten durchführen, um dann auch nochmal die wahrgenommene Latenz zu reduzieren. Problem ist natürlich, dass man das auch gleichzeitig wieder darauf beachten muss, wie leistungsfähig ist dann das Client-Gerät. Das kann natürlich dann auch wieder zu Problemen führen, beziehungsweise zu anderen Kompromissen, die man gehen müsste.
Mhm. Okay, vielen Dank. Ja, ich denke, das ist ein spannendes Feld. Eine weitere Frage, auch von Anonymous, derselbe oder ein anderer. What would be the steps to convert your approach to a stereographic AR experience?
Die Übertragung,
ich denke,
also ich würde es jetzt mal so verstehen, die Übertragung quasi auf eine der AR-Brillen wie zum Beispiel Magic Leap und Unreal.
Ja.
Im Endeffekt wäre bei uns, glaube ich, jetzt die Hauptkomponente, die da problematisch ist, der Videoplayer, weil der jetzt zum Beispiel noch nicht, die Bibliothek ist noch nicht ausgelegt, um auf der Magic Leap zu laufen. Da müsste man dementsprechend nochmal Arbeit reinstecken, aber am Ende ist es eigentlich also in Anführungszeichen kein Problem, diesen Ansatz auch auf andere Systeme zu übertragen. Also jetzt sind wir halt schon in der Hinsicht ziemlich frei, ob wir jetzt Android oder iOS nehmen. Die Tests haben wir mit dem Galaxy S9 durchgeführt. Wir könnten das aber auch auf einem iPhone laufen lassen. Und im Endeffekt hapert es bei uns quasi einfach nur an der verwendeten Bibliothek, um das auf eine der Brillen zu bringen.
Okay, vielen Dank. Ich hätte auch noch eine Frage, und zwar, wenn ich es richtig in Erinnerung habe, haben Sie auch im Paper ja schon darauf hingewiesen, dass es nicht so ganz klar ist, woher diese große Differenz zwischen, was Sie den Client und den Laptop nennen, diese Differenz bei der Latenz. Können Sie trotzdem ein bisschen was dazu sagen? Und was vielleicht also auch noch ein Hinweis, auf dem Laptop werden doch sicherlich dieselben Video-Libraries verwendet wie auf dem Client, also Video.
Genau, wir hatten den VLC-Medienplayer benutzt und der basiert auf der gleichen Bibliothek wie den Player, den wir in den Client integriert haben, um halt auch diese Vergleichbarkeit herstellen zu können. Man hat aber bei dem richtigen VLC, also wenn ich das erstmal mich aufs Video beziehe, da haben wir halt den Fall, wir haben bei dem richtigen VLC-Player nochmal wesentlich mehr Optionen zur Verfügung, die jetzt teils bei uns in der verwendeten Medienplayer-Bibliothek nicht angewendet werden können. Dadurch haben wir dann jetzt in dem Moment die höhere Latenz bei der Client-Anwendung. Bei dem Laptop war es dann wiederum so, warum jetzt die lokale auf dem Server ausgeführte und die beim Laptop über WLAN die Latenz ein bisschen höher ist, vermute ich, dass da anscheinend noch irgendwelche Zusatzverarbeitungen vielleicht von dem VLC-Player auf einem Windows-Rechner durchgeführt wird. Bei dem Laptop sind wir dann ja noch zusätzlich bei LTE komplett drüber hinausgeschossen. Da haben wir halt beim Audio eine Latenz von circa 4 Sekunden. Da war dann die Vermutung, dass das verwendete LTE-USB-Modem einfach diese geringe Datenmenge, wir haben halt Audioimpulse abgeschickt, und dass diese geringe Datenmenge des Audioimpulses von diesem USB-Modem einfach überhaupt nicht priorisiert wurde und deswegen dann die hohe Latenz da zustande kam.
Okay, vielen Dank. Ich denke, im Interesse der Zeit, dass wir jetzt nicht aus dem Plan laufen, sollten wir an dieser Stelle abbrechen. Vielen Dank nochmal, Herr Börner, für Vortrag und Fragen. Ich habe beim vorigen Vortrag auch vergessen zu sagen, stellen Sie sich jetzt einen Applaus vor, den wir im Normalfall im Hörsaal jetzt gehabt hätten.